Section 3 for Chapter 3 is all about temperature. So I hope that you got a little chuckle from this chemistry fun. Temperature is a measure of how hot or cold an object is. Very different from heat. Keep that in mind. Heat comes later in the year. In science, degree Celsius, the degree symbol in C, and Kelvin are the common units for measure. There is Fahrenheit, but we don't usually use that in chemistry or science. The Celsius scale sets the freezing point of water at 0 degrees Celsius and the boiling point at 100 degrees Celsius. The Kelvin scale, sets the freezing point of water at 273.15 Kelvin and the boiling point at 373.15 Kelvin. The difference between those is still about 100. So, absolute zero is something, you may have heard of it before. It shows us the difference between Celsius and Kelvin. Absolute zero is when we reach 0 Kelvin, which it's never been done before. They're working on it. They've reached about 3 or 4 Kelvin as of right now. But you see, that's really cold because 0 Kelvin would be negative 273.15 degrees Celsius. And that's about negative 459 degrees Fahrenheit, just for some reference for you. Okay, but absolute zero is when all movement stops. And so it's very hard to get to that because molecules are always moving. Even though you don't think they are, they are. We're getting to that later. Okay, so for us, we are going to convert with temperatures mainly this chapter. Okay, so these are your 4 equations that you get to use. These 4 equations are not on your assignment about temperature conversions, so you're going to need to look at your note packet, but they will be given on the test, exactly like this, for you. Okay, a couple notes here. With these problems, it might be a word problem, it might not be a word problem, but if you notice, degree Celsius equals this, Fahrenheit equals that, Kelvin equals that, all the way down the line. So the left side of the equation is what you're solving for. So if you need to make a little note so that you're solving for it, whatever's on the left side. So if I want to know Kelvin, then I'm going to look at the left side and say, oh, I should probably use the third equation. Okay? Then the right side, where we have Fahrenheit and Celsius and Kelvin, the right side of the equations is where you plug in your numbers. Have you ever heard of the phrase plug and chug before? Plug and chug is what they used to use all the time when I was in elementary and middle and high school. Apparently not so much now. But you're going to plug the number that you're given into the equation and then chug, solve to find your answer. Okay? So the hardest part in all of this, first off, is picking the right equation. And second, order of operations. That's also key. Okay, so we're going to use these 3 equations to help with example 4. Example 4. The first one we have 95 degrees Fahrenheit, and we want to know how much degrees Celsius that is. Okay, so we have Fahrenheit, look at the unit, have Fahrenheit, and we want the degrees Celsius. So we're solving for degrees Celsius. So we need to find an equation where we're solving for degrees Celsius and we can plug in Fahrenheit. Well, hopefully you chose that we are going to use the top equation to do this problem. Okay, so going back to our problem, I have that my degrees Celsius is equal to, and it's 5/9 times, where it says degree F, we're just going to plug in our 95. Plug in your temperature. And then inside the parentheses still, it's minus 32 degrees, 32.0, and that's it. Okay, so now we're going to have to solve. Order of operations tells us that we need to solve the inside of the parentheses first. Okay, so I still have my 5/9 times 95 minus 32 is 63. And so now we can do the multiplication. You might be thinking, how am I supposed to plug in 9/5 into my calculator? And my calculators for my room, all you have to do is take 5 divided by 9, and then when you get that answer, leave it in there, and then just hit times 63. And when you do that, you get 35. At this point, if you did all this work, you would still miss half a point, because in my class, units are especially important. Okay, so we need a unit on our 35. Well, we are solving for degrees Celsius, so that's going to be our unit, 35 degrees Celsius. All right, next part. We have 100 degrees Celsius, and we want to find Fahrenheit. So which equation gives us Celsius on the right side and Fahrenheit on the left side? That would be our second equation, is what we're going to use this time. So, plugging into that equation, I have my Fahrenheit equals 9/5 this time times our degrees Celsius, so I'm just going to plug in 100. Then the parenthesis gets closed, and we add 32. So this time, since the 32 is not included into the parentheses, we're going to do the whole multiplication dividing first, and then add at the end, order of operations. So, to type this in your calculator, we're going to take 9 divided by 5 times 100, and you should get that that equals 180, and then we still have to add our 32. So 180 plus 32 gives us 212, and our unit, because unit labels are super important, comes from the original problem, and that will be degrees Fahrenheit. In case you didn't know, that's the temperature that water boils at. All right, next one. 25 degrees Celsius is what we have. So it's going on the right. And we want to know K. K stands for Kelvin. So we want to find the Kelvin. Okay, this time, which equation do we use? Well, we want Kelvin, so we're going to have to use our third equation down. Isn't that nice how that's working out? Okay. So plugging into the equation, K, Kelvin, is equal to, I'm going to plug in my degree Celsius number for degree C, so 25 plus 273.15. This one is simple addition, so when you add those two together, we get 298.15. And our unit this time is just going to be a K. You don't need a degree sign. It's Kelvin, not degrees Kelvin. And that's that. Last but not least, we have 117 Kelvin is our half, and we want the Celsius. So by looking, I'm not going to flip to it, but that is the last equation on our line. So our degree Celsius is equal to our number for Kelvin that we have, 117, minus 273.15. When you subtract those, yes, you're going to get a number that is negative, because we have negative temperatures all the time in the wintertime, so I just wanted to show you that it's still okay in science to have a negative number. That's it for our temperature conversions. On your assignment for this, I throw a couple hard ones at you where you have to have two-step problems, and we'll do one together in class if we need to. But the two-step problems are when you have to use two of the equations to get your final answer, not just one. Really making you think, okay? Oh, but we're not done with the notes yet. We're going to keep going just a little bit farther. We have quantitative and qualitative measurements, okay? So quantitative measurements are measurements that deal with numerical data. Quantitative really sounds like quantity. So if it has a quantity, if it has a number associated with it, it is quantitative. So for example, your temperature is 100 degrees Fahrenheit. You have a fever. It has a number, so we can say that's a quantitative measurement. Qualitative depends on the quality. It's very descriptive. So a qualitative example would be you have a fever, or the solution is cloudy, or the sky is blue. We have no numerical data associated with that measurement, and so that's just describing, so it's qualitative. We also have to deal with accuracy and precision in chemistry. How close the measurement is to the actual or true value of what's measured is called accuracy. So how close is it? How accurate are you? And precision is a measure of how close to a series of measurements they are to one another. So the actual value is not considered when measuring precision. You can be very accurate but not precise. Or you could be very precise but not accurate. Or you could be both. Or you could be neither. So this kind of shows you that, okay? So we have our accuracy, inaccurate, and then precise and imprecise. So let's say we're shooting a bow and arrow, right? And so accurate means that we hit the bullseye. Precise means that all of our trials, all of our arrows that we shot, all hit within the bullseye too. They're grouped together. So it's accurate because it hit the mark, and it's precise because all tries are grouped together. Moving right, we're inaccurate because we didn't hit the yellow bullseye, but we are still precise because they are all still grouped together. You're inaccurate, but you are precise with your inaccuracy. Down here, we can be accurate where we are pretty close to the center of the bullseye, but we're not precise because they're not grouped together very well. And then we can be both inaccurate and imprecise because we didn't hit the middle very well for accuracy, and they're not very grouped together well for the precision. So we have those kind of things to think about. Okay? We are not shooting bows and arrows in chemistry, sorry. We are going to be accurate and precise when we're doing our measuring. So we learned about our lab equipment. When we measure the volume of a liquid, should we use a beaker or a graduated cylinder to be the most accurate and precise that we could be? Hopefully you said graduated cylinder, because the graduated cylinder has the markings that allow us to get a better reading of what the volume should be, better than a beaker, which has less markings than the graduated cylinder. Whenever you read the volume in a graduated cylinder, you always want to read to the bottom of the meniscus. The meniscus is the part where it's kind of like filled in, and it kind of looks like a U. So when I draw the meniscus of something, I kind of make it a more extended view, where we would read at the bottom of that U. That's our total measurement. The reason why it creeps up and is curved has to do with surface tension, and we'll learn that later on. A little bit more. Error. We make mistakes. Everybody makes errors. When we are in lab and we take measurements, the accepted value is the correct value based on a reliable reference. So I would give you the accepted value. The experimental value is what we measure in the lab. So we can take that difference between the two, and that gives us our numerical error of the results. We also have something that's called percent error. Percent error is the percentage that you had error. So you take the absolute value, that's what these vertical lines mean, of the experimental value minus the accepted value. And then once you subtract those two and take the absolute value of it, you divide by the accepted value and you multiply by 100. And that gives you the percentage that you were off. In our labs, we like to have very low percent error. Error means you want to have 0%. You don't want to be messed up at all. And so a 0 to 5% error gives you a mole bug. So whenever I have you calculate this out, you want to have less than 5% so that you get that extra mole bug. All right? So now we are finished with part 3 for chapter 3. We are going to work on specifically the temperature conversions assignment, and then we're going to use the percent error equation in our next lab.